Chapter 13 focuses on ethers and epoxides, which are two types of functional groups. In this first video for Chapter 13, we will go over naming ethers, the physical properties of ethers, and the synthesis and reactions of ethers. Now, an ether is a functional group where you have an oxygen that's attached to two R groups. And if you recall from Chem 226 or first semester organic chemistry, R stands for any sort of carbon-containing group. So this here is an ether. We'll start by learning to name simple ethers. Simple ethers are when you have straight chain alkyl groups attached to either side of the oxygen atom. Now the general rule for naming an ether is you name the two groups attached in alphabetical order followed by the name ether. So let's go ahead and take a look at this first example. Now we have a 3-carbon chain attached to the oxygen, which I'll indicate here. Now for 3-carbon chains, we call those propyl groups. We also have a 2-carbon chain attached to the oxygen. A 2-carbon chain is known as an ethyl group. So the name for this molecule will be ethyl propyl ether. Let's do one more. Here we have an ether where we have two 2-carbon alkyl groups attached. So we have an ethyl group and an ethyl group. Now when the two groups are the same, we use the prefixes such as di, tri, tetra, etc. So in this case, we're going to be using di, since we have two of the ethyl groups, diethyl ether. And diethyl ether is a very common organic solvent that's often used in labs. Now in more complicated ethers, we can actually treat the ether portion as a substituent or as a branch of a longer chain. So in this example here, we have our oxygen attached to 2-carbon chain, and then it's attached to the second carbon of a 4-carbon chain. So this is not just a butyl group. This is actually a sec-butyl group. But to make it more easier to name this ether, what we're going to do is we're going to treat the oxygen and the 2-carbon chain as a branch. And since this is a 2-carbon branch, we're going to go ahead and call this an ethoxy group. Now our ethoxy group is on the second carbon of our 4-carbon chain. So we're going to go ahead and number these carbons. Now we're treating this as an alkane. So we'll go through the naming rules of naming alkanes. So we're going to go ahead and label the location of our ethoxy group, which is on carbon number 2. And then we end with the parent chain name of our alkane, which is butane. So we get 2-ethoxy-butane. Another example is when you have ethers that are attached to benzene rings. Now again, in these cases, we're going to be treating our oxygen and the chain that it's attached to as a branch of our parent chain. And we're going to think of our parent chain as the benzene ring here. So we have a 1-carbon chain and a 2-carbon chain with an oxygen involved. So this would be known as a methoxy group. And this again would be an ethoxy group. Now, as far as numbering, we want to give the substituents the lowest possible numbers. Now, no matter how we number around the benzene ring, we're going to have one substituent on carbon number 1 and one on carbon number 4. So we can either go 1, 2, 3, 4, or 1, 2, 3, 4. So since there's no difference in the way that we number, we're going to go based on alphabetical order. So carbon number 1 is going to go to the ethoxy group, and 4 will go to the methoxy group. Then we will go ahead and name our molecule. So we get 1-ethoxy, 4-methoxy, benzene. And benzene is our parent chain name. As far as the physical properties of ethers, we're going to be focusing on their relative boiling points and their solubility in water. Now, ethers contain an oxygen. Our oxygen has 2 sets of lone pairs. We have this bent shape around the oxygen. So we do have a slight dipole in the direction of the oxygen atom. Now, this dipole does make ethers slightly polar. However, depending on the number of carbons you have in these R chains, it can decrease the polarity of the overall molecule. Now let's go ahead and compare ethers to alcohols, their closest relative. Now in an alcohol, instead of having 2 R groups attached to the oxygen, you have 1 R group and an H. Now this H is important because it means that alcohols are capable of participating in hydrogen bonding. Now, even though ethers can accept a hydrogen bond from something that has hydrogen bonding, so for instance, this alcohol and this ether could hydrogen bond with one another, ethers themselves cannot hydrogen bond with each other. So ethers have dipole-dipole interactions, which are weaker than hydrogen bonding interactions. So for the most part, ethers have lower boiling points than alcohols. And related to that, with solubility, when we're talking about solubility in water, the ability to hydrogen bond significantly increases the chances of being soluble in water. So again, since our ethers do not have that hydrogen bonding capability, they can accept a hydrogen bond with water, but they're not going to provide any hydrogen bonding interactions with water. So since there's less hydrogen bonding interactions with ethers, they're going to be less soluble than alcohols. Okay, so ethers have lower boiling points, they're less soluble in water. Now what that means is ethers actually make great solvents. So they're often used in the labs. And the reason that they have great solvents is because of their low boiling points. So they can be easily evaporated. And because they have a lower solubility in water, it means that they're more nonpolar, and that means that they can dissolve most organic molecules. So ethers are actually very useful in the lab. There are 3 main ways to synthesize ethers, and all of these will be great review from OChem 1. So in our first method, it's called the dehydration of alcohols, and they are acid catalyzed conditions. So in our first method, we're going to be using 2 alcohols. So we'll start off, we have an alcohol with a lone pair on our oxygen, and we also have acid catalyzed conditions. So that means we have a lot of hydronium ions floating around in the solution. So first what's going to happen is our oxygen is going to take one of the acidic hydrogens from hydronium, giving the electrons to the oxygen atom to give off water. Now what we're doing here is we are creating a good leaving group in this molecule. So remember that OHs are bad leaving groups because they're strong bases. So now we're setting up this molecule for an SN2 reaction. So at this point, a second alcohol molecule will come in, and the alcohol will act as our weak nucleophile. Okay, so remember that it's a weak nucleophile because it is neutral, does not have a negative charge. So our weak nucleophile will come over, our oxygen will attack the carbon containing the leaving group and kick off our leaving group in the form of water. Now we have this intermediate here. We still have a positive charge on this oxygen. So our last step is going to be removing this extra H. And we can either have water or another alcohol molecule can come in and do that. I'll just go ahead and show the water that we just kicked off. We'll come in and take the H, give the electrons back to the oxygen. This is a way of creating diethyl ether. Now there are a couple of limitations with this dehydration of alcohol method. The first one is you can't make unsymmetrical ethers. So in our previous example, we showed the formation of diethyl ether, which involved two ethanol alcohols. So in this example here, we would have an ether that has a 2-carbon chain and a 3-carbon chain. So that means you would need two different alcohols. You would need ethanol, which would provide the 2-carbon chain, and you would need it to react with propanol, which would provide the 3-carbon chain. Now the problem with this is you can't tell the ethanol and the propanol that they can only react with one another. What ends up happening is they can react with themselves to create a mixture of products. So we can end up with our desired product, which is our unsymmetrical ether, or two ethanol molecules can react with each other to create diethyl ether, or two propanol molecules can react with each other to create dipropyl ether. So with this method, we would end up with a mixture of products. The other limitation is that it can lead to elimination products. So we saw in OChem 1 that anytime you have an SN2 reaction, you have the potential of having E2 reactions also occur. So in this example, we could go through the steps of having an SN2 reaction or setting up an SN2 reaction, but we can see that an E2 reaction could also occur. So again, starting off with our alcohol, which is a bad leaving group, can go ahead and take the acidic hydrogen from our hydronium and create our good leaving group. Now, instead of having our second alcohol come in and act as our weak nucleophile, it could also act as a weak base. So it can take the H on the carbon adjacent to the carbon containing the leaving group. Then the electrons would go in the direction of our leaving group to form a double bond and kick off our leaving group. So instead of an SN2 mechanism, we could have an E2 mechanism also occur, which would create an alkene. And the third limitation of the dehydration of alcohol method is that it's really limited to primary alcohols. We saw in OChem 1 that secondary and tertiary substrates don't really work well in SN2 reactions because they're too sterically hindered. So our second method for synthesizing ethers is the Williamson ether synthesis. Now this reaction is also an SN2 reaction, but instead of involving a weak nucleophile such as an alcohol, we're going to be using a sodium alkoxide, which can come from an alcohol, but is a strong nucleophile. And we can react that with an alkyl halide, sulfate, or sulfonate. And this is going to act as a primary or secondary substrate with the good leaving group. So we're setting this up for an excellent SN2 reaction. So let's go ahead and take a look at the mechanism. Now this is a two-step reaction. In the first step, we will start with an alcohol, which we know is a weak nucleophile, and we're going to treat it with a strong base such as sodium hydride. Now sodium hydride is a hydride ion, which is a hydrogen with a lone pair and a negative charge, that is stabilized by a positively charged sodium ion. Now hydride is a very strong base. It cannot act as a nucleophile because it's too small. So our hydride is going to come in and it's going to take the H from the alcohol, which is relatively acidic, and we're going to give the electrons to the oxygen atom. Now the oxygen will gain a lone pair, which will give it a negative charge, and now this negative charge will be stabilized from the sodium of the sodium hydride. We will also create hydrogen gas, which is very favorable because it can just bubble away. Now, this product right here is known as a sodium ethoxide. And the ethoxide ion is a much stronger nucleophile than our original alcohol. So now our ethoxide will act as our strong nucleophile, and we can put it in the presence of an alkyl halide, such as a 3-carbon chain containing iodine, which is a good leaving group. Now the ethoxide will come over, attack the carbon containing our leaving group, kick off our leaving group, and again this is an SN2 mechanism. And this is one way that we can create an unsymmetrical ether. So we have a 2-carbon chain and a 3-carbon chain here. So step 1 is first forming that sodium ethoxide, the strong nucleophile, and step 2 is reacting it with a substrate that contains a good leaving group. Now our last method for synthesizing ethers is actually a little bit of a review. It's involving the oxymercuration-demercuration reaction. Now we talked about this in OChem 1 as a reaction with alkenes. Now we mainly use this reaction to create Markovnikov alcohols without the risk of rearrangement. So for example, using this alkene here, we're going to treat it with our oxymercuration-demercuration conditions. Now the water acts as the nucleophile and will attach at the Markovnikov position, which is the more substituted carbon of our alkene. Now in this example, we're going to create an alcohol. Where we have the OH group here. Now, this reaction is not only limited to using water as the nucleophile. We can also use other weak nucleophiles such as methanol or ethanol, so any sort of alcohol. So we can take our alkene, treat it with the same conditions, the mercuric acetate. Instead of water, let's go ahead and use methanol. And then follow it up with sodium borohydride. Now the product we will get from this is, again, we're going to have our group on the Markovnikov position. But instead of an OH group, we're going to get an OMe group. So it's the same mechanism as we saw in the alkenes chapter. So if you've forgotten that, go ahead and take a look at the beginning part of your book and see how the mechanism proceeds. But this is another way of making ethers. As far as reactions of ethers are pretty mild. They don't do a whole lot of reactions. The only thing they really can do is they can be cleaved by strong acids to produce alkyl halides. So for example, we can take an ether, treat it with a large concentration of strong acids such as HBr. We'll produce 2 alkyl halides as well as water. Now, as far as the mechanism for this reaction, it's very similar to the formation of ethers using acid-catalyzed conditions. So in our ether, we have an oxygen with the lone pair. When it's placed in the presence of a strong acid, the lone pair can act as a base, take that H, and kick off the bromide as a leaving group. What we're doing here is we're turning our oxygen positively charged, which is going to make the group a better leaving group. Now the bromide ion that we just kicked off is a good nucleophile. And what it's going to do is it's going to come in and attack either carbon that's connected to the oxygen. It doesn't matter which one, they're both ultimately going to react. So we'll just go ahead and choose the one on the right first. So we'll attack this carbon, kick off the electrons, and give it to the oxygen atom. Now at this point, we have formed our first alkyl halide. We also have ethanol. So now since we have an excess amount of acid in the solution, the ethanol will continue to react. So the oxygen will take the H, kick off the bromine. We're turning our bad leaving group into a good leaving group. And then the bromide that we've just produced is going to act as our good nucleophile. It will attack the carbon containing our leaving group, kick off our leaving group in the form of water, so we lose water. And we create our second alkyl halide. Now let's do a couple of practice problems. And as always, I invite you to pause the video, try the problems on your own, and then restart the video to check your answers. So in problem 1, we have a 2-step reaction involving sodium hydride and an alkyl halide. So this is a Williamson ether synthesis. So in our first step, our sodium hydride is going to act as a base to remove the H from our alcohol. I'll just go ahead and draw in the intermediates just so we can see what's occurring. But in these problems, we just really need to write the answer of the product that is produced. So the sodium hydride will remove that H and will create our strong nucleophile with the negative charge on the oxygen. Now this can act as our nucleophile and attack the second portion of this reaction, which is a primary alkyl halide. So it'll come in, attack the carbon containing the leaving group, and kick off the leaving group. Ultimately, what we will produce is an ether where we've added 2 more carbons to the oxygen atom. So again, this is a great way to make an unsymmetrical ether. In problem number 2, we have the same reaction conditions. We have sodium hydride as well as an alkyl halide. Now let's go ahead and take a look at this. Now, even though the point of this problem is to draw the product, let's draw the mechanism and any intermediates just so we can make sure we're doing everything correctly. So again, our sodium hydride will remove the H from our alcohol. And again, we create a good nucleophile. Now our nucleophile is going to react with our substrate. Now it's important to note that we have a leaving group on a tertiary carbon. So this is a tertiary alkyl halide. Now the Williamson ether synthesis involves an SN2 mechanism in the second step. And what we learned in OChem 1 is that tertiary alkyl halides cannot do SN2. So we have a good nuke, which is also a good base. So in this case, These reagents are not good for a Williamson ether synthesis. We're actually going to have an E2 mechanism occur. It is too sterically hindered for our nucleophile to attack this carbon and kick off the leaving group. So the product we're actually going to end up with is this elimination product here. So you have to be very careful. Even if a reaction asks for you to draw a product only, it's important that you understand the mechanism so that you make sure you get the correct product. And lastly, we have a version of the oxymercuration demercuration reaction. We are using ethanol as our weak nucleophile, so the oxygen will be attacking the carbon that is the most substituted. So we will end up with this as our product. And again, to see the mechanism of this reaction, go back in previous chapters and look up the oxymercuration demercuration reaction.